Hello and welcome to Inside Exercise. I'm Emeritus Professor Glenn McConell. Just finished a great chat with Professor Håkan Westerblad from the Karolinska Insitute in Sweden. He is one of the biggest names in the world in muscle fatigue. He's done 30 or more years of research. He's done a lot of mechanistic studies, but we also talked about more applied things. So what causes fatigue during, a 30-second sprint, a 10-second sprint, a marathon? Does lactic acid cause fatigue? Does lactic acid cause muscle soreness? Comparing and contrasting eccentric type muscle contractions to concentric muscle contractions. What causes fatigue in the heat? By its very nature, talking about fatigue can get complicated at times, but you'll see I've got timestamps. So you can see what time, we're talking about the mechanisms, what time we're talking about more applied things. So you can skip around a little bit. I really think you'll enjoy this one, so stick around. Hi, Håkan. How are you? Thanks for coming on Inside Exercise.
Yeah, hello. I'm glad to be here.
Oh, good. So Håkan's from the Karolinska Insitute, and which has been, really big in exercise science for decades now, or even longer. And the Karolinska Insitute is where the Nobel Prize is awarded every year. So there's been a big history there. But I guess is it fair to say that some of the power, some of the presence in exercise and metabolism research has shifted towards Copenhagen, so still in Scandinavia, but
yeah, I think that would be fair to say that some of it has gone to Copenhagen. We still do quite a lot of exercise, both at the Karolinska Institute and then also at the Sports University in Stockholm.
Yes,
but it's not as central as it used to be. I think Copenhagen has taken over quite a lot of it.
Well, I couldn't help thinking about that because it just so happens you're the third in a row after having very little Scandinavian influence. There was, Jorgen Motocheski, and then Abigail Mackie, who's actually Irish, but she's in Copenhagen, and now you. So this is the attack of the Scandinavian researchers, yeah.
Mm-hmm.
So you're semi-retired. So tell me, how's that working for you? When did you, become semi-retired? What are you doing nowadays to keep busy?
To keep busy, yeah, I've been semi-retired now for almost half a year, and it's actually great.
Yeah.
I do quite a lot of running, long distance running. I can do that when there is light outside. Used to do it very early in the morning, in the dark, at least on the dark part of the year. Now you can do it when you want to. Yeah. And the last few years too, I've been head of department, which means it has been a lot of administration, which was interesting, and I haven't done that much of that stuff before. So that was 5 interesting years, but now the administration is down to basically 0, and on the part I'm still working, I can do things I like.
Okay. So you're writing?
Writing papers about the studies that we have concluded, but haven't had time to finish writing and so on. So I really do the enjoyable stuff these days.
So with the long distance running, I can't help thinking quite a lot of the people I've had on, they've sort of come through a sort of a sports background and then become involved in academia. Did you come through that route, or were you more sort of in the academia and then took up the exercise and the running?
I've always been very interested in sports, but I had to finish early. I got sick when I was around 15 and couldn't really do. I did some cross-country skiing and running, but then I stopped that for 35 years and took it up again when I was around 50.
Wow.
And so that's good, because many of the competitors that used to be good, they can't really run anymore.
You've saved your knees and whatever.
Yeah, so I saved everything, yes, for later. So now I can enjoy that.
So how much do you do? Like what sort of, I don't know, mileage, kilometers?
I'm running around 300 kilometers a month.
Oh, I thought you were going to say a week. Okay.
No, not
that
a
would
week.
Be, yeah, of course not. That's a lot. That's like 70 kilometers a week. That's a lot. Okay. All right. So I guess when you're doing that, sometimes you feel fatigued. Yeah. So this is the way we've got you here, because you've been just for decades now, the man or one of the main people in fatigue that I've been aware of. And, I sent out with the Twitter, your most cited paper is, 6,000 sites or something on fatigue. So were you always interested in fatigue, or is that something you moved into?
Scientifically, this is where I started during my PhD studies. It was about fatigue, and it has been a central theme throughout, and the related stuff, fatigue recovery, and the relation to the training adaptations.
Yeah. So I guess we should first of all define fatigue. What is fatigue in your mind? I know it's complicated, and there's various different definitions, and people have written chapters on it. But, why don't we just set the scene? What are we talking about when we're saying fatigue?
Yeah, it's really complicated, and you can look at it from many different angles and so on. The way we do experiments and so on, I would say that fatigue is when you have a decline in physical performance during exercise, and then you get fatigued. Of course, you will sense this fatigue immediately if you do very hard exercise, so you're close to your maximum capacity. On the other hand, if you do submaximal exercise, muscles and you sort of get fatigued, but you don't slow down. You just have to put in more mental effort to continue at the same speed or whatever you're doing when you get fatigued.
That's true. Yeah, so I guess it's a loss of your ability to do what you want to do, I guess. Well, that's if it's, as you said, if it's sort of more maximal, but if it's submaximal, you wouldn't even realize that you're necessarily getting fatigued. You'd just be less able to produce force or power or whatever than you would have been at the start, but you don't actually necessarily even realize that. Is that right?
Yeah, something like that. If you take a marathon, for instance, if you start and your aim is to do it at a constant speed, it's going to be pretty easy for the first 10, 20 Ks, then it's a bit tougher, and then towards the end it's really tough. But you can still, if you do plan it correctly, go at the same speed.
Exactly.
So you're clearly fatigued, but you're doing a submaximal exercise, and then it's fine anyway.
And I guess if we're talking about what are the potential sites of fatigue, you mentioned there, it's be harder to exercise or whatever. So I guess there's a whole line of potential places. When you look at the textbook, it'll talk about, the brain and then the spinal cord and whatever. But what would you say are the main sort of sites that you think are playing a role in fatigue?
Yes, if you start when you do physical exercise and so on, the first thing in the chain is that you have the motor system, the brain, various areas in the brain that then form the signals that's going down to the nerves that activates muscles. And so it could be, of course, a site for fatigue is the central parts there, the whole motor system gets sort of fatigued. And then signal goes down to the motor neurons, out to the muscle, and then inside the muscle fibers, you can also have fatigue. So that despite the nerve, the brain is sending down the same signals, the muscles can't respond to it. They have become slower and weaker.
And actually, one thing I was thinking about was exercise and the heat. This could be an example where, because there's always a bit of a controversy, is fatigue central? Is it peripheral? What do you think of exercise during the heat? So it could be a bit of an interesting one.
Yeah, that's an interesting, generally interesting question. This debate has gone on forever if fatigue is central or peripheral. And in my mind, the brain and the muscles, they do know what they do, so to speak. They collaborate in an excellent manner most of the time. So it's not that the brain decides that, well, I don't want to do this anymore. I think it gets input, or it does get input from the muscles saying that we can't cope with it and so on. So there you have situations. I think there is always a component of central fatigue. even if you're really peripherally fatigued to a large extent, say towards the end of a 400-meter sprint, you have severe peripheral fatigue, but mostly the last few steps you can still produce a bit more power in most cases, but you can only do it for a few steps, and you can always spurt. Towards the end of a marathon you can spurt, but you can only do it very for a short period. So there is always a central component. And then coming back to your heat question there I think you have other inputs to the brain too. For instance, the brain will sense if your body temperature increases, because that's dangerous. And then you will have a central component, because when you contract your muscles, you generate heat. And if you're too hot to begin with, the brain will sense that this is not a good idea to continue to produce even more heat. So there you have central fatigue, turning off the muscles so that you don't get overheated.
Yeah, I'm really annoyed because I can't remember the name of the person. It's a female, did the study from Denmark. I think she showed this really nicely. She got people into the heat chamber and they exercised to exhaustion. So the same workload, and they rode a bike to exhaustion 10 days in a row, which is quite remarkable. You know, they do all sorts of full-on studies there. And she found that they'd go to a certain temperature and then fatigue, and then they were getting like heat acclimated. So each day they came back, their body temperature would take longer to get to that same point, but it would get to that same point they fatigue. It was like 10 days in a row, you see the same, it was 40.7 or something was this sort of magic number that they all stopped at. So it seemed, you know, it's not definite, but it did seem to suggest it was central, as you said. So that was pretty interesting.
Yeah, that's also, I mean, everyone knows that if you do prolonged exercise in the heat and you cool down your head, it becomes easier to run or bike or whatever.
Yeah, hang on a minute. You cool down your hand, is that what you said?
Head.
Oh, head. Oh,
head.
yes.
Yeah,
okay.
the hand. No, not the hand, the head.
You know, I was thinking of, because we used to do this prac at Melbourne University, and you'd do something to the whole body, and then you'd stick your leg in cold water or something, and then you could trick the receptors or something. I thought you were talking about that. So you're saying if you cool the head, yeah.
Yeah, I think maybe it works with the hand too, but I think it's more.
It's a bit more helpful.
It's better with the head, because the temperature sensors, they are in the brainstem, and so then if you cool down your head, then you fool the system. So the brain now thinks, oh, fine, things are fine again, so we can continue at a higher speed, generate more heat from the muscles, and in that way it feels easier for a while. And if you're really good at cooling down your head during exercise, you may fool the system to an extent so that it becomes really dangerous. You just continue to generate heat from your muscles, because your body is not really going to cool down when you cool down your head.
That's true, yeah. So I was kind of forgetting that. So you often see people in marathons or whatever, and it's really hot, they'll just pour water over their head. Exactly.
Yes.
They prefer to do that than drink it when it gets to that certain temperature. All right.
I think it's much more effective to cool down the head than to drink it, because when you drink it, it comes down to the stomach, where the senses aren't really, and then how much difference does it make to the body temperature when it comes in the stomach, and how much can you take before you start to vomit or something like that, because of all this crude fluid that comes down.
All right. So the other thing I wanted to talk to you about was eccentric contractions and concentric contractions, the different sort of fatigue, different sorts of contractions. So maybe just if we explain a little bit the difference between eccentric and concentric, and then what's happening sort of metabolically and you know, even with muscle soreness and whatever. Is that something you want to?
Yeah. So the concepts there is well, people tend to give complicated names to something that's really not that complicated. So concentric contraction, that's a contraction when the muscles are shortening. And eccentric contractions, it's sort of strange really, but it's a contraction when the muscles at the same time are lengthening. So if we take its simplicity, If you run uphill, then you use basically only concentric contractions. You have to shorten your muscles to work against gravity.
Yep.
On the other hand, when you run downhill, it's a lot of eccentric components, because then gravity wants you to run even faster. So you brake, you use your muscles to slow down instead.
Exactly.
And so you have, with the eccentric contractions, metabolically, it's not that demanding. It's more that you're exposed to really high forces when you do these eccentric contractions. And whereas when you run uphill, then it's the forces are less, but the metabolic component is much bigger. I mean, you breathe more, your heart rate goes up a lot more when you run uphill than downhill. So that's an easy way of knowing if it's metabolically demanding or not.
Yeah.
So then when it comes to the next step there, that when you do the concentric contraction, running uphill, that's a typical endurance kind of exercise, an endurance training component. Whereas when you run downhill, on the other hand, then it's not metabolically particularly demanding, then it's more strength training. And when you also do resistance strength training, eccentric contractions, when you, not when you lift up something, but when it comes down again, then you have eccentric contractions and so on.
Yeah, and this is where people quite often want to with resistance training, they want to focus sometimes on the eccentric, because you can actually produce more forces, right? So at first that seems confusing to people, but if you think about really simple, if you've got a weight and you're doing a bicep curl, then when you're lifting it up, it's concentric, the muscle's shortening. And when you're lowering it, but not just dropping it, but lowering it slowly, that's eccentric. And everyone would know that you could obviously handle a heavier weight lowering it. So, if you had the most weight you could lift up, and then that was it, and then someone gave you a heavier weight, you could obviously lower it. It would be hard, but it would be low. So you can do higher forces. And then what actually is the result from that? So, a couple of days later, what happens if you've been doing concentric versus eccentric exercise?
Yes, if you have done purely concentric, then a few days later, you may still feel a bit weak in your muscles and so on, but you don't really have any soreness. Whereas if you have done uncustomized, eccentric contractions that you aren't used to, you haven't done exactly this thing before, then from a day after and so on, you have severe muscle soreness, delayed onset muscle soreness. So that really comes with the eccentric contractions and not with the concentric. Yes.
Actually, just thinking about it, I just spoke last week with Abigail Mackey from Copenhagen about that sort of stuff. So there's a little plug for that podcast. You can go and have a look at that one as well. Now, the interesting thing is people will often think, oh, lactic acid, oh, I'm sore. It must be all the lactic acid. What do you say to that?
No, it's not. The lactic acid is gone. And I don't think it has anything at all to do with this prolonged soreness. Maybe lactic acid, hydrogen ions, and some other things during acute exercise make this uncomfortable sensation in muscle. But it's clearly not causing any prolonged soreness.
Yes.
And you have all these acid metabolites that you're supposed to get rid of with massage or well, things like that. I don't think they exist. And clearly they're not going to disappear with whatever maneuvers some people believe in.
Exactly. So no matter what you did, if you did that most lactate producing, I still reckon the 400 meter, we're very run centric. I'm an ex-runner and you're a runner. So we keep giving examples running related. But yeah, 400 meter run on the track is about the highest lactate you ever get. And probably, I don't know, 100 meter sprint or 50 meter sprint swimming. But the point is, no matter how high you get that lactate, it's going to be well gone within half an hour, a couple of hours. It's not going to be 2 days later.
No, correct? Exactly. And also the alternative is, of course, when you have these really high lactate levels, they may trigger something that then appears a day later. But I think there's rather convincing evidence that that doesn't occur either. the soreness, the prolonged delayed onset muscle soreness comes from eccentric contractions and
Correct.
sort of miniature maybe problems in the muscles. They're not damaged in any way, it's just maybe a way to try to convince yourself that it's not a very good idea to do exactly the same thing a few days after you've done something that caused this soreness.
So we're talking mainly focusing on peripheral muscle fatigue is your work.
Yes, so the research I've been doing has been on peripheral fatigue. It's focusing on mechanisms inside muscle fibers. So the brain and the nervous system doesn't really come into play in our type of experiments.
Yeah.
So we are the nervous system. When we press the button on the stimulator, the electrical stimulator, we trigger action potentials in the muscle fibers and they contract. Yeah. But still, of course, from a general perspective, I'd be interested in the central versus peripheral fatigue and things like that too. But I haven't really studied it.
Yeah. So your research has mainly been in, is it mouse isolated muscle, or?
So the sort of the big thing with my research is that throughout the years we always used intact single muscle fibers.
Of course, yeah.
So that has been the preparation. And when I started in '84, then people were working with frog muscle fibers. We used Xenopus frogs. My mentor, John Lenegren, who I did the PhD with, he was sort of an expert on this, building chambers to measure force and all the bits and pieces required to do the single fiber experiments. So people were using frogs because they were fairly easy to micro dissect. You dissect looking down the dissection microscope, forceps in one hand and the scissor in the other hand. The scissors are the scissors used during eye surgery, and the forceps is for repairing watches. Once upon a time when people still repair their watches.
That's true.
So you could rather easily do that on frog fibers. So that's where we started, and everyone said it was impossible to do it on mammalian fibers because of too much connective tissue and technically difficult. So people had tried over the years and said it was impossible. I decided to sit down a summer and see if it was possible, and it turned out that it was. So from there on, we skipped the frog fibers, went over to mouse toe fibers. And then subsequently, we've done the same thing in other mouse muscles and rat muscles, and more recently, human muscle. So it's doable in all four we've tried. And the basic fatigue mechanisms basically are the same.
Okay, so that's important. You find basically the same sort of causes of fatigue, etc., in all the preparations you've used.
Yes, we have looked at a lot more mechanisms and so on in mouse fibers, but the general patterns and so on, everything we have looked in more than one of the species, it's the same. Okay. It's not so mouse muscle fibers generally fatigue more rapidly than rat fibers. And the human fibers are more fatigue resistant than the rat fibers. But the mechanism, sooner or later they fatigue, and the mechanisms now seem to be more or less identical. And the same with the frogs.
So that's important because I mean, obviously the first thing people wonder is, oh, how applicable is this to humans? And you're finding it's pretty similar.
I hope so. I mean, because no one would really be interested by single toe fibers in the mouse fatigue. Exactly. Well, the mice maybe, but they won't read the papers.
That's true. So with the frog and the mouse, are you getting a whole intact fiber? Then with the human, you'd just be doing it from a biopsy. So it'd be like the ends of the fibers would be, broken, etc. Yeah.
No, because if the ends are broken, then you can't use it in the kind of experiments we have. So in the humans, we got intercostal muscles from thorax surgery. And there you could get complete muscle fibers out with the tendons on both sides.
Beautiful. Okay.
So if you cut the muscle fiber, it's from our perspective, it's dead.
Yeah, exactly. Right. So, you know, there's various questions, obviously. So we've got some from Twitter, etc. But let's get to those in a bit later. How would you summarize? So, you know, if we try and make it practical. So someone's doing a sprint. Yeah. What would you say is causing the fatigue in that? So I was going to say 10 seconds, but that's, you know, 100 meter sprint if you're like the best in the world. You know, there's obviously metabolic things. And I meant to say at the start, thank you for writing the chapter for the book that I, you know, put together, that I edited on exercise metabolism, where you spoke about metabolic factors in fatigue. Maybe you can tell us a little bit about, you know, what's happening there metabolically, and, you know, I'm sure it's complicated, but, you know, why are they slowing down so much at the end of a 100 meter sprint?
So if we exclude the nervous part of it and central fatigue, and I would think that at least people good at running 100 meter sprints, it's peripheral that limit the performance to a large extent. And the way we see it is that when you do something highly intensive like that, you use a lot of anaerobic metabolism. And when you use anaerobic metabolism, you would have fatigue inside the muscle fibers. So if you do something more slowly and you use only aerobic metabolism, then you can go on for a very long time without having any fatigue. But as soon as you get anaerobic metabolism, it comes. And the two major things there with anaerobic metabolism is that you break down phosphocreatine, with the end products being creatine and phosphate ions. Yes. Creatine ions most likely do nothing, but the phosphate ions are central to all energy requiring processes. It's one of the products. So you drive the motors, cross bridges, and the pumps pumping ions inside the muscle fibers with ATP, which breaks down to ADP and phosphate ions. And if you have too many phosphate ions, basically you don't want to go drive that reaction as fast. So that's one thing, breaking down phosphocreatine to creatine and phosphate ions. And the other one is that you break down glycogen, the glucose units, and the mitochondria aren't fast enough to take up all the pyruvate, so it goes to lactate and hydrogen ions instead. I think lactate ions do very little, but the hydrogen ions, acidification, can do something. And they were classically the cause of fatigue.
Great.
But what we have shown rather in many experiments is that the hydrogen ions, at least in our case, do close to nothing on muscle function.
Perfect. Right.
So the answer of your question is that I think it's phosphate ions inside the muscle fibers that slow you down at the end of a 100 meter sprint.
All right. So maybe just to summarize that a bit. So I guess the creatine phosphate, as you said, is the creatine and the phosphate combined, they break apart, releasing energy, which is used to do the contraction. And it's very important during very high intensity exercise. And it only lasts, I don't know, 6 or 7 seconds. It's a bit debatable, I guess. And then you're saying that energy is used for the contraction, but the phosphate that's come from the creatine phosphate, which is called inorganic phosphate, is playing a role, you think, in fatigue. But at the same time, you're also getting more of that energy, which is anaerobic, from the breaking down glycogen, which it's too fast to go into the mitochondria and get, you know, used aerobically. So it's going to lactate and a hydrogen ion. And you're saying the lactate's not probably playing much of a role, but the hydrogen ion may be playing a role, but in your hands, it's not. Is that a fair summation?
Yes. Good summation.
And so with the phosphate causing fatigue, is it the phosphate causing the, I know that inorganic phosphate causes fatigue, you know, when you add it in your preparations, etc. But is it partly just that the creatine phosphate's running out and you can't get the energy as quickly from breaking down the glycogen to lactate as you can get from creatine phosphate? So are you partly slowing down because you can't get the energy quickly enough, or is it the inorganic phosphate causing fatigue, or a bit of both, you think?
I think it's both. And in severe fatigue, when the phosphocreatine is going down and you continue high intensity exercise, then at least in our hands when we looked at it, then you might have a situation that during each contraction, ATP will go down a bit. Normally ATP stores stay basically constant.
Yes.
Luckily, because if that went down to really low levels, then we will kill ourselves during exercise, and that's not a very good
Rigor
idea.
mortis. Yes, yes.
Yeah, yes. So that mustn't happen.
Mm-hmm.
But at any rate, during contractions, when you have very or no phosphocreatine left, basically, you can have a decrease in ATP and transient increases in ADP.
Right.
And the ADP then is known to slow the cross-bridge cycling rate.
Okay.
So that would reduce the speed of shortening. And at the same time, the phosphate ions is reducing the force that the cross bridges can produce.
Okay.
So together, they then ADP reducing the velocity, phosphate reducing the force, and the power you need to run is the force times the velocity. So both go down.
Okay. Yep. Yep. Wow. And you'd be aware, you know, people are quite into having creatine supplements. So if you, I was doing a little bit of this work at one stage. So if you take creatine supplements, it does indeed increase your muscle total creatine, and about 2/3 ends up as, you know, creatine, and about 1/3 goes to creatine phosphate. So you do top up your creatine phosphate. So that should enable you to go, I don't know, half a second or a second longer, perhaps.
Mm.
You know,
Yeah, so
before you
that,
drop the speed. Sorry. Yeah.
Yeah, I think so. If we believe that, then it's you get deplete the phosphocreatine stores, and then the cross bridges are becoming slower. If you have more of it, then you should be able to do 1 or 2 steps more before this slowing occurs, which
Yes.
in a 100-meter race is enormously important, of course.
Exactly.
On the other hand, you will get more. If you have more phosphocreatine, you will have higher concentrations of phosphate.
Yeah, I was just thinking that.
The other side of the coin.
Exactly.
But there it seems like you have a logarithmic scale. So if you start at the resting inorganic phosphate levels, you increase a bit, it has a big effect. And the more that you increase, the smaller the additional effect is. And
Okay.
with normal phosphocreatine levels, you reach phosphate levels that are sort of maximally inhibiting. So if you increase it further in the short term, 100-meter sprints, it seems not to matter.
Okay.
So then you have the positive effect from having fast cross bridges longer, and you don't add up more negative effects. And the end point is that you go slightly faster.
Nice. All right. The other thing that I remember was in the textbooks, but I've never read up on it, was the idea that breaking down creatine phosphate buffered a little bit hydrogen ions. Is that right or not?
Yeah, that's right. It's just straightforward biochemistry, I think.
But again, you would say, because I wanted to get back to that, you would say the hydrogen ions, so the acidity. So we're talking about the, you know, the lactic acid being broken down to lactate and the hydrogen ions. You're saying that's not important. And is it correct that the studies that show that it was important in fatigue were done at very cold temperatures, and when they were done at warmer temperatures, it seemed like it wasn't playing a role? Is that part of the idea?
Yes, that is part of the idea. So traditionally, well, the easiest way to see if something has an effect on contractility in muscle fibers is to do skinned fibers. So we are using intact fibers. Skin fibers you can take away various parts of it, but say you take away the surface membrane, and then your solution is the intracellular solution. And then when you add the hydrogen ions, force and speed went down. But the skin fiber experiments were difficult to perform at physiological temperatures. So people always did them at 15, 20 degrees or something like that. And then hydrogen ions have a big effect. But when they learned how to do these experiments more towards the physiological body temperature, 30 degrees and above, then the effect was very little. But having said that, it's still debated. And the thing that still remains to be solved is that the combination of increasing phosphate and hydrogen ions may affect force production and shortening velocity even at the physiological temperatures. So there are skin fiber experiments suggesting that. And then we have our intact fibers suggesting that's not really the case. But that's still debated, and that's for the future to really see why intact and skin fibers don't really show the same thing.
All right. And what about this idea that lactate itself, if anything, can be a little bit protective? Is that, it seems like you...
I'm not an expert there. The papers I've read about what lactate does, my brain's take-home message, so to speak, is that it didn't really do anything.
Okay.
But it could be because, well, I could be biased. I don't think it's likely that it would do anything, and therefore I read things so that it didn't do anything. But of course, it's osmotically active, so it will attract water and so on, so that may do something.
Yeah, and a thing that I wouldn't mind bringing out, even though it's not related to fatigue, is that people tend to think of, lactate as this terrible thing, and if you could take a pill and get rid of lactate, you'd be really happy. But that's really not the case, because lactate, can diffuse out. It can be carried into adjacent fibers, carried to the liver, converted to glucose, and it's actually a good thing. And I remember there was a study in the 80s or something. They actually blocked gluconeogenesis, so in a rodent model, so they couldn't convert lactate and other things in the liver to glucose. And they did about, they fatigued about 30% earlier or something. So lactate is, I guess you're saying it's inert probably in terms of fatigue, but it's actually probably a good thing because it's supplying carbons and energy to other muscle fibers and to the liver, etc.
And also it's a very good marker, because if you do exercise above the aerobic, so you have to use anaerobic metabolism, then the lactate and hydrogen ions are exported out of the muscle fibers, and you can measure the lactate easily in the blood. So you will know if, and then you have, in most cases, a rather good correlation between how much lactate you have in the blood and the muscle fatigue status.
Exactly. And nowadays there's all this...
And you can't really, so if you want to look at that, lactate is excellent, even if it maybe doesn't do anything inside the cells. Whereas if you want to measure the phosphate, inorganic phosphate ions, you have to take a muscle biopsy, because it's not exported out. So you can't measure it outside. So it's pretty useless as a marker.
And there's also, I'd get killed if I didn't mention this, but there's also evidence nowadays that lactate's doing all sorts of things, affecting appetite and all sorts of things now. So I think we just have to mention that before George Brooks gets upset with us. All right. So what about other things? So, just for people to understand, so when you're contracting a muscle, there's calcium released from something called the sarcoplasmic reticulum, and that's important, very critical for the contraction. And, the other thing is calcium release and calcium uptake, etc., can be affected during contraction and may play a role in fatigue. Could you comment on that at all? Or?
Yeah, so we think calcium is really a central player. And there it's important, like you mentioned there, calcium is released inside the cells. It's stored in the sarcoplasmic reticulum, released to the normal fluid inside the cell, where the motors are and so on. So that's the way to activate the contractile machinery. And then it's pumped back into the sarcoplasmic reticulum. So it doesn't leave the cell, or the cell have their own stores of calcium. So they just move from one part to another. And there, I think in acute fatigue, we were talking about that you mustn't get depleted of ATP because then the muscle fibers die.
Mm.
And there one can say that calcium is very, very important because the muscle fiber seems to have various mechanisms so that if you are in a metabolically rather critical situation, the calcium release starts to decline or more or less stop. Mm-hmm. Which means that if calcium is not coming out of the sarcoplasmic reticulum, you don't activate the energy consumers, the motors and the pumps anymore. Mm-hmm. Which means that you can't deplete ATP. That's impossible. You turn yourself off via turning off calcium. And there seems to be many fatigue-related mechanisms that inhibits the sarcoplasmic reticulum calcium release.
And this is a good time to actually mention, I'm pretty sure you did some of this research, working out what percentage of the muscle energy which is being produced is actually going into the contractions, and how much is actually going into these pumps you mentioned. So, you've got calcium pump, which is pumping the calcium back into the sarcoplasmic reticulum so you can then release it again to contract. But you've also got these sodium potassium pumps, which are maintaining the membrane potential, etc. I mean, it's actually quite high. It's controversial, I think, but it's up to like 50% or something, isn't it, of the energy which is used for pumps versus what's going into the contraction itself.
Yeah, I think in that ballpark. The cross bridges, the motor use about 50% of the energy and pumps about the other, and it's these sarcoplasmic reticulum calcium pumps that dominate. So okay. About 5% or so of the energy is used by the sodium potassium pumps.
Okay.
And a lot more. But that is controversial. In mouse fibers, doing the experiments we do with repeated short maximum contractions, tetani, and then a break and then a contraction again and so on, then it was up to 70% or so being used by the sarcoplasmic reticulum calcium pumps and 30% by the motors. But then I think mice with their short legs and so on, relaxation, which depends a lot on pumping calcium back very rapidly, is critical. If you try to run fast with short legs, you have to be able to relax rapidly. And in our hands, the capacity of the SR calcium pumps is about 10 times more than normally needed. So they have a great reserve there and pump calcium enormously effective. So in the mouse, it was 70-30. In humans, I would guess more like 50-50. 50% to pumping and 50% to cross bridges. But then there are others that believe it's a lot more on the cross bridges and less on the pumps. I think that is because many of these experiments are done with continuous contractions. And that's not really interesting for normal exercise where you do a short contraction, rest, short contraction, rest. And the pumps are going all the time, whereas the cross bridges only are activated and consume energy when you contract. And then there is zero energy consumed by the cross bridges, whereas the pumps pump also in the resting periods.
Okay. So can you give a rough idea? I know this is complicated because I'm trying to sort of apply it to real, I talked about the 100-meter sprint and whatever. When with the calcium, so if you did like a 400-meter race where we all know, lactic acid running, lactic acid's through the roof, people often like throw up sort of 3 minutes after when the lactate, when the hydrogen ions get to the highest level in the blood. Say a 400-meter sprint, say, 400-meter race, you can't sprint the whole way. What's causing the fatigue there, do you think? So, you go out too fast and you die, you slow down or whatever. What do you think's going on there?
Yeah, I think the calcium is then becoming really important during the last 100 meters or so of a 400-meter sprint. And you can see even the highly competitive people, since it's an Olympic medal at the finish line, but still they go very, very slowly, or relatively speaking, slowly towards the end there. And that is most likely, I can't prove it, that's very difficult, but it must be that the muscle fibers protect themselves by turning off the calcium release. And then you of course, the most fatigable fibers turn off first, and towards the end you have the slow twitch, very fatigue resistant type 1 fibers. They probably continue. On the other hand, the speed you can run with them is much less than the speed you can run when all the fibers are working properly.
Exactly right.
So
now, I guess, sorry, we hadn't really talked about that. So in the 10-second sprint, we know that the people that are best at that are going to have a lot of fast fibers. Yeah. And they are very fatigable. And they won't have much slow twitch, which are much slower contracting and less fatigable, but they're not much good to you if you want to sprint. Yeah. Is that fair to say?
Yeah, exactly. And then if you're most likely the 400-meter people are also on the speed rather than the endurance side. But then of course they know that you can't start at your 100-meter pace. If you're going to run 400 meters, you have to start slower. And then the idea is basically you should reach the 400-meter finish line with some power left in your fast twitch fibers. So all of it shouldn't end after 370 meters or stuff like that, because that's not a very good idea.
So what do you think's causing this calcium release problem towards the end of a 400-meter race?
That is something we when we started to measure calcium during fatigue, we saw that it declined rapidly towards the end when the fibers went towards exhaustion. And then we tried a lot to find the mechanism behind this. And it turns out that it's probably more than one mechanism, several different mechanisms. And maybe the most important one, but that's something we haven't been able to prove really, is that we have these phosphate ions again. So they accumulate in the cytosol, in the intracellular cell water. And if you have enough of them for a long time, and most likely if you combine it with sort of a general energy crisis, then they enter the sarcoplasmic reticulum. And inside the sarcoplasmic reticulum, you have lots of calcium. And if you combine calcium and phosphate ions, and the concentration of the two of them goes high enough, you have precipitation, calcium phosphate precipitation, which means that you bind the calcium there so they can't be released anymore. And calcium phosphate precipitation is a very, very complicated thing. It comes in different versions. Some that it's just enough to stir for a second or so, if you have them in solution, and then they come back in solution to the stones outside, which never come back into solution, basically. So it could be that the phosphate ions, you have calcium phosphate precipitation in the sarcoplasmic reticulum. That could be maybe the major mechanism. We've tried to find a way to show that this is the case, but haven't succeeded this far.
And how long does that precipitation last for? So if you're doing like repeated sprints, so if you're doing high intensity intervals and then recovering and then going again, you'd like to think, you could keep going.
My gut feeling, so to speak, is that it's if you don't overdo it, it will come back again to a large extent. And if you you do your sprint and then you rest for a while and then it's fine, and then you do the next sprint and you rest for a while. But if you overdo it, so you really go longer than you think is a good idea. I tried it on myself running uphill. So you run uphill and then it goes so slowly because you have such a severe sensation of fatigue, and then you decide to go slightly further, and then you can sort of force your muscles into some kind of state where they don't want to contract anymore. So if you then continue to run slowly, it's you don't feel that much. The breathing and heart rate goes down, but you just can't get the muscles going again. And then I think you overdone it. So then you have a calcium phosphate precipitation in a form that takes maybe hours to dissolve and come back again.
Yeah, so that makes sense. So if you're running the 400-meter final at the Olympics, where you just don't leave anything to at all, then obviously for hours you wouldn't be able to perform well. But if you're doing 400-meter repeats, where you're going a little bit slower and whatever, then you're not going to have that same level of crisis, I guess, in the muscle.
Yeah, maybe.
All right. So what about if we think longer term? So we haven't really thought about muscle glycogen, because even though some people think, oh, I need to be carbohydrate loaded for everything I do, really muscle glycogen is not going to run out. So the classic studies, Hermansen showed a 30-second sprint. You can do like a Wingate, where you go flat out from the first pedal for 30 seconds on a bike. You can actually use about half of your glycogen in that 30 seconds, which is remarkable, but you're still not depleted. And during submaximal exercise, say 60-70% of VO2 max, it would take about an hour to use that much glycogen. So it's amazing. But again, it's not really probably going to cause fatigue. But what do you think about when you go, it's 70% of VO2 max or something. So something that a trained person can go for about 3 hours or so, if they're not drinking carbohydrate. The glycogen gets down pretty low. Do you think the glycogen itself, depletion, again, I don't know if you've looked at this, so apologies if not. Do you think muscle glycogen depletion is causing fatigue, or you think it's other things that are actually associated with that?
I think during prolonged activities, clearly glycogen depletion is an important component. And there it becomes technically complicated in that if you just take out a piece of muscle and measure the glycogen, it's not going down to, it's going down a lot, but not really down to zero.
Exactly.
If you, on the other hand, look the distribution of glycogen in the fatigue state, it turns out that it's much more reduced in certain parts. Within the myofibrils, it can go down a lot, and also between myofibrils, it goes down a lot. Whereas the ones, the glycogen stored close to the surface doesn't really change that much. So I think you have, before the total goes down to zero, which it doesn't do, you have in certain spots, it's going down a lot more. And also if you, we have shown, for instance, when glycogen gets low during prolonged activity, you inhibit the sarcoplasmic reticulum calcium release.
Okay.
And is it because glycogen is then low, mainly in the intramyofibrillar space, which seems to be the important part, and that sort of gradually decrease the SR calcium release. The alternative is, of course, that it's generally low in this space, but at the channels, the ryanodine receptors, some of them have no glycogen attached at all, so to speak. So when it's coming down to low level, it's lowish everywhere, but it can be basically zero in some spots. And then maybe you turn it off there. And there I think the mechanism, when the glycogen is low during low intensity exercise, you enter the acute fatigue state in this particular small spots. And you have the same mechanism as you have in high intensity exercise, but they come much, much later with phosphate accumulation and all this and that.
Okay.
So I think glycogen is very important during prolonged low intensity activities.
Yeah, and it's a metabolic thing as well. So, the classic studies like from Coyle showing if you exercise 70% VO2 max to exhaustion, your carbohydrate oxidation starts to drop. And then if you drink carbohydrate drinks, for example, you can maintain your carbohydrate oxidation and go longer. So I guess there must be more than just that sort of muscle glycogen, a sarcoplasmic reticulum sort of nexus thing going on there, I guess. There's also the metabolic. You know, if you drink carbohydrate, you can keep going, but you're not affecting the glycogen levels.
Maybe not, but if you do drink glycogen, doesn't that mean that you don't have to use your glycogen stores, because now you have the glucose coming from somewhere else?
The classic studies doing cycling anyway, it doesn't affect the glycogen use. It doesn't spare glycogen. They used to think that. It doesn't spare glycogen. So the glycogen ends up the same, you know, on a crude level from the biopsy. And then they can go like an hour longer without, supposedly, looks like they're not really using much glycogen. They're just using the glucose uptake to keep their carbohydrate oxidation going. That's what it looks like.
Okay.
Yeah.
Yeah, but maybe it's this, I'm trying to say the same thing more or less, that you need energy from carbohydrates. And
Yeah,
if
you're
you
getting the
don't have
energy.
any glycogen, but you get it then from somewhere else. Because if you don't have carbohydrates to drive energy consuming processes, then only fat remains.
Yes.
And the maximum speed that you can use the fat is lower. Although it feels like with in severe endurance exercises, people can go on at a really high speed for forever, basically, which means that if you really train it, the fat oxidation part can be very effective.
Exactly. So even though you get energy slower from fat, if you've trained a lot, you can actually increase your maximum fat oxidation rate. Exactly. So if you're going for a long time, you can sort of keep chugging along. Great. All right. Now, I saw you did something on, actually, before I get to that, I need to mention, we've mentioned sodium potassium pump. I think it would upset Mike McKenna, the former, you know, where we used to work together at Victoria University, the director of the institute there, if we didn't talk about the potential of potassium playing a role in fatigue, yeah?
Which, of course, that's one way to inhibit sarcoplasmic reticulum calcium release. So the sequence there in muscle fibers is that you have action potentials, go on the surface, go into the interior of the fibers via the T-tubular system, and they trigger calcium release from the sarcoplasmic reticulum, which means if you have problems with propagation of the action potentials, you will get fatigue. And surely this can happen. In our experimental conditions, if we continuously stimulate the muscle fibers at a rather high frequency, you do have action potential problems, failure, which reduces the sarcoplasmic reticulum calcium release. So that's clearly, it's not debated at all, I would say. The debate is more is this going to be an important component during normal kind of exercise? And it feels in the way we do the experiments and so on, it seems not to be very important. In human exercise, in most human exercises, I don't think it's that important either, but at high intensity exercise, it can, of course, contribute.
Yeah, because you do get, so just to clarify for people, so you're getting this action potential where you've got the electrical potential being moved. So the nerve comes into the muscle, you know, and there's electrical potential coming down the nerve, and then it has to travel along the muscle. And the way it does that, you have sodium coming into and potassium out, and then the sodium potassium pump has to redress that and get it back again. And we know that that's not actually during intense exercise. It's not been matched perfectly, because you do get potassium loss, and the potassium can go like from, say, 4 millimoles per liter in the blood up to about 8, yeah, during high intensity exercise. So there is definitely some potassium loss, and it's messing up that membrane potential and therefore the action potential. Is that fair enough?
Yeah, that's fair enough. And even I talked about the T-tubules, that are sort of very, very tiny tubes going into the interior of muscle fibers. So if you swim in a T-tubule, if you're small enough or you're 9, then you are outside of the fiber, despite the fact that you're in the middle of a fiber.
Oh, of course, yes.
So when potassium comes out into the T-tubules, you come out in a very narrow space there. So when action potentials travel down the T-tubules, you will have a potassium accumulating in the T-tubules. And there it will reach much higher concentrations than you can measure in the blood. And there they could definitely limit action potential propagation and calcium release. So then the big question, does this happen during human exercise, if you're interested in human exercise or not? So that's something that have attracted a lot of attention in many, many studies. And I don't know, I think the general take-home message is that it's, in most cases, it seems not to be very important.
Okay, all right. Now, we've talked about, as you said, you've focused on the muscle and you haven't really conducted studies outside the muscle, which is fair enough. You can't look at everything. But I did mention to you before we came on air about mental fatigue. And you said you'd actually done some work on that. What was that in regards to?
If it's mental fatigue, and it was done on mice, so it's at least it's sort of the brain component of it. We did a study some years ago, which haven't really attracted that much attention. It was Ivarsson et al. In 2017. At any rate, we had observed that if you give mice nitrate, that the muscle fibers then will, you can store more calcium in the sarcoplasmic reticulum after a while when given nitrate, which means that you have more calcium to release, which then means that at submaximal contractions, you have the same brain input to the muscle or activation, but you get more force. So from that, we then also found studies showing that mice love to run on running wheels. So there was a team in England that put the running wheels in parks, and the mice came there.
I saw that.
Voluntary and ran. So we had running wheels in the cages of mice, on control mice and mice that were given nitrate, and then most likely at submaximal contractions, which you use all the time. For instance, during running, they would be stronger with the nitrate. And it then turned out that the mice with nitrate ran more on the running wheels than the control mice, 15–20% more. And they ran more because each time they were running, they ran faster. So the time spent on the wheel was the same, but they ran faster, most likely then because you have the normal input from the brain, but now you get more force of it. And they don't have any clocks or anything like that. They run at what the brain decides is a comfortable running speed. So they ran faster when they had the nitrate. And then after 3 weeks of nitrate, they were more fatigue resistant, so you had a better endurance training for them than the control mice. But then they even more interested. So apparently, if you are stronger, so to speak, in the muscles, it's more fun or more comfortable to run, and you can run faster. And then we took away the nitrate after 3 weeks when they were actually more fatigue resistant. And then the running speed slowly came down, or over 1–2 weeks, came down to the control level again, which means now they were running at the same speed as the control mice, so it didn't matter that they were more fatigue resistant. They sort of mentally didn't care about that. But now the muscles, when you put the same signal from the brain, the muscles produced less power and you ran slower. Meaning that if you have sort of fresh muscles, you really feel like it's a piece of cake running, then it's more fun to run and you run slightly faster.
That's really interesting, but I must have missed what was the central, how did you know it was the central, not the peripheral effects of the nitrate supplementation? I must have missed that.
So I think the nitrate, in our mind, they had a peripheral effect.
Mm-hmm.
So they made the muscles
easier.
stronger, made it
Mhm.
easier, yes. And the brain didn't really understand that. So the brain sent down the same signals as always. And then the output was a high running speed. So it was not that the brain realized, at least not in these mice, that, oh, we're stronger now. We don't have to activate as much as we used to. They activated the same.
Okay. So how's that mental fatigue though? I must be slow. I must need some nitrate or something.
Well, it's because many times the people that really need to exercise and so on for health benefits and so on, I think due to various reasons, it's hard for them to exercise. Mm-hmm. Because when they try to exercise, you have to put in a lot of mental power to do it. Okay. It's not comfortable at all. So then in some way, if you can make the muscles become stronger and the mental effort to do the exercise is not that severe, then it's more likely that they will exercise.
Okay, because you're saying
I think
that it's voluntary running. Yeah, exactly.
Yeah,
so because
exactly.
it's easier, they've decided to run more. Okay, yep.
And now, I think that would go with humans too, because it's if each time you try to exercise, you have to put in a lot of mental effort. Mm-hmm. Then most people, they don't like to put in a lot of mental effort into exercise.
No. All right, so we've talked about fatigue a lot, but the topic is fatigue, recovery, and the training response. Can you flesh that out a little bit more? So the recovery part and the training response parts and what you've done with that.
Well, that's something we've focused, that's been in most of our focus in recent years, looking at the recovery part, which is also, it's not, muscles aren't recovering by one mechanism. There seems to be several mechanisms involved. And when it comes to the training response, at least if you're on a sports level and so on, then it's the critical balance between how much you can train so that you don't overtrain your muscles, you have enough time for recovery on the one hand, and the more you train, basically, the better the adaptation, the training adaptation. Mm-hmm. So there you have the balance there. You should train as much as you possibly can, but still have recovery balancing it. Mm-hmm. So you're not sort of killing your muscles with too much training. And that's something we've looked quite a lot at.
Right. So what have you found with your recovery research? What's a couple of messages you got there?
So with the really acute exercise, like your 100-meter sprint and so on, I think most of the recovery process is that normalize the metabolic disturbance that occurred. Get rid of the hydrogen ions and rebuild the phosphocreatine. And then you're basically, at least if you look at maximal contractions and so on, back to normal levels again, which will take them minutes, 30 minutes or something like that, and you're basically back. Maybe you can't probably do another 100-meter sprint at the same speed, but still, a lot of recovery has occurred. But then if you do more severe, longer-term exercise and so on, you frequently go into another state where mainly at submaximal contractions, you have a problem. And this problem can remain for hours and even days after a single bout of exercise. And that was when it's originally found in human muscles. It was called low-frequency fatigue, due to the fact that it was observed when you stimulate at low frequencies, whereas when you have maximal frequency stimulation, muscle force was basically back to normal. And there, from a central perspective, a nervous perspective, you use your muscles more or less always at submaximal frequencies. So when you have this, which was called low frequency fatigue, you need to put in more mental effort to get the same power output from your muscles. The low frequency fatigue concept has been used in all sorts of situations now. So people don't really know what it is anymore. So we have tried to introduce the complicated, longer version of it, prolonged low frequency force depression, PLFFT, complicated enough not to be misused, we hope. And to more clearly say what it's all about, that it takes a very long time to recover at in the submaximal contractions. And there you have different...
Sorry, you go.
And there we found at least 3 different mechanisms behind this.
Which, did you want to elaborate on those?
Yeah, yes.
Yeah.
Yeah, and so what we have seen is that you can have prolonged problems with sarcoplasmic reticulum calcium release. Okay. So that's mechanism 1. And then the mechanism 2 is that you can also have prolonged problems with the myofibrillar calcium sensitivity. So even if the calcium comes out of the sarcoplasmic reticulum, you don't get the same force production.
Mm-hmm.
And there it seems to be a fine-tuned balance between inhibition of calcium release and inhibition and reduced calcium sensitivity, which seems very dependent on free radicals or reactive oxygen nitrogen species. And the third mechanism then is you have myofibrillar problems. So you also have some decline in maximum force, but mainly in submaximum force. And that's something in our hands, you mainly see after eccentric sort of resistance training types of exercise. You have microscopic damage, is one would say so, to the myofibrils. Not really muscle damage, which people frequently call them when we look down the electron microscope and so on, and also look at individual myofibrils and their contractility. It's not much. You can't see anything basically in the electron microscope to explain it. So it's really down on the very, very small level. When people have seen big changes in muscle, I think that's because the experiments have been far more severe than would ever happen during normal eccentric contractions.
This fits really well with, I just had Abigail Mackey on from Copenhagen, and she was saying she did studies and she'd have elevated creatine kinase in the blood, etc. So she'd be all excited to go in there and look at the muscle damage, and she couldn't see anything. So similar. Now, I've been actually wondering when we could slip in about reactive oxygen species and things. I know you've done work on that. So people would be familiar with the term free radicals. But yeah, reactive nitrogen species and reactive oxygen species. Maybe you can just explain that like a little bit and then say what you think's going on. And then I know you've done studies using antioxidants, which people would have heard of.
Yeah, I think the antioxidants are much more known than the free radicals, and an awful lot more known than the reactive oxygen nitrogen species. Mm-hmm. So people know that antioxidants are good for you, so to speak. Which our research, if I'll take the endpoint, so to speak, show, and not only ours, but many others too, that antioxidants aren't really good for you if you have too much of them. But at any rate, during exercise, especially intense exercise, you produce reactive oxygen species. The mitochondria produce some, and you also get it from other processes in the muscle fibers. NADPH oxidases are the sort of popular ones these days, but maybe we shouldn't go into a lot of details there. And then the other free radical you have during exercise being produced is nitric oxide, NO. And the oxygen part and the NO part can be combined. If you have both of them, you can get peroxynitrite, which is a free radical that can do change properties of the proteins and so on. So the thing with all of these reactive species is that they're very reactive. When they form, they will react very rapidly, some of them extremely rapidly, within fractions of a second, with something that they find. So in that case, they produced somewhere in the cell and then immediately react with whatever they found in the neighborhood.
Mm-hmm.
And so if you have too much for too long of these, you clearly will have problems in cells generally, in the muscle fibers. And that might be something that happens in disease conditions, chronic inflammatory diseases and so on. You have an elevated baseline production, which is not very good for you. But when we come to exercise, you have a burst of
Yes.
these reactive species being produced during exercise. And then there is nothing again. And then you have another burst. And that seems to be an excellent trigger of adaptation towards more endurable fibers.
I think you explained that really well. And I've done some work, you may know, with nitric oxide, and trying to explain in a grant how, you know, you can have elevated free radicals, so reactive oxygen species, elevated nitric oxide during exercise where it's short, so temporal increases, which is like, could be a good thing for signaling, etc. But then, you know, and then at the same time, you're trying to talk about how people with diabetes, for example, and heart failure can have elevated nitric oxide and reactive oxygen species, you know, the whole time, and that's a bad thing. And it's hard to kind of explain that. Yes, and then
no, it's not putting gasoline on the fire, so to speak. It's the other way around. So
exactly,
if you have a fire and put on gasoline with bursts of really high, then you would expect that the thing explodes basically, and it's really dangerous. But it turns out that the gasoline in this case really take away the fire instead.
Exactly, and it's hard to explain though. So there, you know, people think, okay, so let's throw antioxidants at them, you know, because they just think free radicals are a bad thing and whatever. And you did touch on there that you know, some giving too many antioxidants can have a negative effect. Did you want to elaborate on that a little bit?
Yes, so I think to begin with, since these reactive species are so important, all the cells in our body have a very, very sophisticated system to take care of them. So you have normal concentrations of all of them. And these systems, the internal, our own antioxidant systems, they are of course located at the right place and take care of what they should take care of. And with the training, also endurance training, you get more of the antioxidant defense. So what we've seen then, if you add the antioxidants from the outside to disturb this highly balanced internal system. So we try to and also then focusing on recovery. In our hands, the free radicals don't do that much, at least not during acute fatiguing exercise. Prolonged exercise and at submaximal exercise, they may do something, but then during recovery, they're really important. So what we've seen that this prolonged low frequency force depression that I talked about, it can be due to decreased SR calcium release. And that seems to be the major component under normal conditions. So then you have a calcium release problem. If you then turn on or you add a lot of external antioxidants, what happens then is that you move the problem from calcium release to myofibrillar calcium sensitivity. So you don't take away the problem, you have equally poor recovery of submaximal force. But now it's instead caused by myofibrillar calcium sensitivity problems. And then one can say, who cares? And I think the muscle fibers care. Because if you have a calcium problem, then that changes in the calcium cycling inside cells is a very good way of triggering adaptations. So the calcium will activate processes that activates genes transcription, and you try to get rid of the calcium and the problem. So I think that's a key component to the adaptations with endurance exercise. Whereas I don't think the cell can sense a myofibrillar calcium sensitivity problem. So then you just have a problem, but you don't know, you have no way to understand from the cell nuclear perspective that you have a problem, so you don't get any adaptation. This is sort of a black and white picture of it. So if you take enough antioxidants, the cells have problems with recovery if you really do intense exercise, but you don't get any adaptation. And that's something people have shown, for instance, with high doses of vitamin C combined with high doses of vitamin E. You can do endurance exercise and you have no effect.
Less mitochondrial adaptations, etc.
Yeah, exactly.
So
luckily, one could say that you have to take quite a lot of it.
Exactly.
So all these pills that at least in Sweden are advertised as this is good for you and you improve muscle quality and function and this and that. They contain so little, so it's just money down the drain. They're quite expensive for something that is, in comparison to our internal systems, is basically zero. So that's good that you can take them. You spend your money on nothing. On the one hand, on the other hand, you don't get sick from it. But if you really manage to disturb your internal antioxidant defense, then you can have problems, severe problems with endurance exercise. But I think it's been shown also with cancer and so on that if you really manage to add a lot of antioxidants, this can make the situations worse in various cancer forms, and
yeah, I mean,
it should be avoided.
It seems like a lot of these vitamin supplements and things, they end up having negative effects, if anything, when they get studied. I'm not a big fan of it ends up being expensive urine, but I'm sure that's going to upset a lot of people. But all right, so if we can go to Twitter, there was a couple of questions on Twitter. So one was like, what questions do you think need to be answered and what are you excited to look at? But, you're semi-retired now. So I guess it's more, what do you think of the hot, I don't know about hot, but what do you think needs to be examined if you're a young lad coming out and you had all this funding? What would be the main things you'd look at?
Yeah, so I can say that when starting, we tried to find out the cellular mechanism of fatigue. And then we mainly went for the fast twitch fibers that do fatigue. We have studied fatigue also in slow twitch, the fatigue resistant fibers. It's pretty boring because they don't really get fatigued. They just continue to contract forever. So we figured out the mechanism, and more recently we've done quite a lot of human studies too with the electrical stimulation of them and muscle biopsies and so on to try to figure out if the mechanism we observed in the single fibers, if they also occur with human exercise. And there I think an important next step that I would love to do if I was younger is that to use new techniques. So instead of taking, say, a muscle biopsy, and then you mince it up and you measure metabolites and you measure changes in gene expression, this and that, and the whole thing, you divide it into single fibers. And then you measure things individually in humans, then type 1, the slow twitch, the fatigue resistant ones, 2A, the middle ones, and 2X, the really explosive, fast, easily fatigued fibers. So you look at them individually and the training response and so on individually. I think there is a lot of knowledge there on how to train and how muscles behave. Because I think, for instance, when you, with strength training, and you look at the protein changes with the novel techniques when you can look at proteomics and so on, in many cases, not much is happening. And that might well be because, say, in type 1 fibers, some proteins go down, whereas in type 2 fibers, they go up, and you look at the whole thing and nothing happens. Doesn't mean that nothing happens. So that's one thing. And in the cellular environment, it would also be, there were techniques to go a cell is a small thing, but inside a cell you have compartments, or you have round important things like the ryanodine receptor, the sarcoplasmic reticulum release channel. The local environment there, I think, is very important too. So if you could also study that. So not only what happens in the whole cell, but what actually happens in the small parts of the cell. That would also be very interesting. We have looked a bit recently. Something we've been very interested in is also mitochondria and the calcium handling of mitochondria versus the calcium handling in the sarcoplasmic reticulum cytosol. So going into the subcellular system and individual fibers, I think that's where a lot of knowledge will appear with new techniques, since you can now do things that you couldn't really do when I started.
Nice. I think you've made a huge contribution. So can I ask you, how many papers have you had? like
I haven't counted, but the real research papers is somewhere between 100 and 200.
100 and 200, well, that's pretty vague. Yeah.
Yes, yeah, but I should know that.
That's all right.
But I don't. I looked recently, actually, the H value right now. So it's 65, according to Web of Science. There's 65 papers have been quoted 65 times
or more. Beautiful.
So that's a lot better than what I expected when I started my research career.
It sounds like it sounds like you don't worry about your numbers of papers like some people do, like I do. Okay, I'll ask you another question from Twitter. Is there a link? We pretty much covered this. Is there a link between muscle fatigue, lactate clearance, lactate production? So, I mean, we've talked about lactate itself, but the hydrogen ions probably not. Well, lactate's not playing a role, you don't think, and the hydrogen ions probably aren't playing a role. Is that fair to say?
At least not the sensation of fatigue. You know, when you do heavy exercise, you feel awkward in your muscle. And there clearly the lactate and the hydrogen ions most likely have an important role. There are studies showing that if you combine lactate, hydrogen ions, and ATP in the extracellular environment in muscle, then you get the sensation you do get during intense exercise. So there they probably play an important component. There, of course, phosphate have no importance whatsoever because it's inside the muscle fibers, so you can't sense it.
That's interesting. So I always thought that, you'd say I'm running for the bus or whatever, and my legs are burning. It's the lactic, it's the hydrogen ions. Well, it's the lactic acid, people would say. I always thought that was probably not the case, but you're saying that that actual burning feeling could be the, playing a role.
Yeah, I think if you only have lactic acid, so to speak, apparently nothing happens. But if you add an increase in ATP outside of the muscle fibers, I think it's adenosine that is the important component there. The three of them together, at least I've seen in one paper, showing that then you get the sensation. Whereas if you add them individually, you don't.
Okay. All right. So there's one more here from Twitter again. This one is, do the same mechanisms that underlie peripheral fatigue also regulate AMP-kinase signaling? If so, would peak concentrations of ADP and adenogenic phosphate for brief periods play a important role, or area under the curve, etc.? I think we vaguely talked about this a bit earlier. You're not thinking so, yeah?
No, I think the AMP-kinase is a bit complicated there. So from my perspective on how to activate the AMP-kinase, it's supposed to be activated by AMP and ADP. And it clearly is in a test tube. So if you have the protein, the enzyme, and you increase AMP, ADP, you will activate it. But during normal kind of exercises, the problem is that ADP might, in severe, sort of towards the end of a 400-meter sprint, or maybe towards the end of a 100-meter sprint, it may briefly, very, very briefly, within milliseconds, increase, and then it goes down again. AMP may also accumulate a bit, but the concentration is very, very low, and it may transiently increase a bit. So the thing that really accumulates when you have a net breakdown of ATP is IMP, inositol monophosphate. It accumulates, but I don't think the AMP-kinase is supposed to be sensitive to it. Meaning that in the test tube, AMP-kinase can be activated by AMP-ADP. During normal exercise, I'm not so sure. And we, for instance, shown that it can be activated by the reactive species, the free radicals. And that would be, to me, a much better way of activating it, because then you have something that does occur and can have a prolonged effect. Whereas I can't see how a protein can be activated for quite some time with spikes that are only milliseconds in duration. Maybe they can, and maybe I'm wrong there, but I don't think that's the important way of activating it. And then the other question is this really a key player in glucose uptake and so on? And there I think you are more of an expert than I am.
Yes, that's probably thanks for bringing that up. But yeah, I'm not a big fan of AMPK playing a role in glucose uptake or fat oxidation or glycogen use during exercise, but that's not related to fatigue. But maybe that'll be a chat for another day. All right, well, this has been great. Thank you very much for coming on. So, before I let you go, what would you say are the key takeaways, sort of bottom line points you want people to remember from this chat?
We've discussed different mechanisms of fatigue and so on, focusing on what I've done, the peripheral fatigue, what's happening inside muscle fibers. And I think it's gone through that it's a bit complicated. There are many different mechanisms that might occur. And then you also have the central component. We discussed that you have a big central component when you're exercising in the heat. So maybe the big take-home message is that when you do sport activities and so on, fatigue, that you can't perform at the high rate throughout an exercise, is sort of a pain in the backside, and you train to minimize this as much as you can. On the other hand, I think the reason as to why there are many different mechanisms behind fatigue is that fatigue is really something really great, one could say. It's if there weren't mechanisms to stop us exercising when things start to become dangerous, we wouldn't be here. We would be dead, all of us, basically. If you don't stop exercise when you're exercising in the heat, you will break down the muscles, you would have kidney failure and this and that. If the muscle fibers don't turn off themselves, like they do by not releasing the calcium, if you remember that part of it. So they turn themselves off so that the calcium doesn't come out of the sarcoplasmic reticulum. And there are many mechanisms to stop this. If these mechanisms weren't there and the nervous system, the brain, could get going and just activate the muscles that are now having a metabolic crisis, they will, the immediate energy there, ATP, would go down to low levels, so low levels so the muscle fibers will die, which is also, then you have the final spurt. Now instead we have fatigue, which is a much better thing because then we can exercise again the next day.
Correct. And we want people to exercise again the next day. We want them to exercise every day. Hey, so you're training for marathons, yeah? So when's your next marathon?
It's actually the New York Marathon in
really?
In a week, 10 days or something like that. Yes.
Really?
Yeah.
Oh, cool.
So I'm looking forward to that.
Are you in good, I was going to say good nick that we say over here, good shape? You're in good shape?
Yeah, it's reasonably okay, but you never know. I can get a cold or something the last few days, and you have to travel there, which is always complicated.
That's true.
But hopefully I'm in relatively good shape.
You're a modest man, but you told me off camera earlier on, you're 65 and you've run 3 hours 15. Is that correct? That's pretty amazing.
In that ballpark, yes. Well, it's not that amazing.
It's pretty
It's good.
good.
It's yeah, it's good enough for me at least. there are people that are better than I am, but not that many.
Not that many. Perfect. Okay. Well, good luck with that. And thank you again for coming on. It's been great. Thank you.
Yeah, it's been great being here. Thank you.
Good on you. See you. Bye-bye.
Bye-bye.
I hope you enjoyed this podcast. Please like, subscribe, pass it on to your friends and colleagues. Check out the other podcasts. Thanks again.